Now let us start the discussion for the estimation of causal model. As we discussed in week 9, that's the first week after the midterm, in order to interpret a slope coefficient in a linear regression model as the causal effect of the random variable, we need to tell a story about how y is generated. And the story that we tell should make it reasonable that the slope coefficient is how much y changes when x is changed, holding all other factors constant. So it's important to imagine this change happening without other things changing at the same time. Otherwise, you won't be able to, if other things are also changing at the same time that x is changed, then the coefficient of x will not reflect how much y is changing. So therefore, the causal effect is kind of a ceteris paribus effect, meaning that the effect of changing x holding everything else constant. Next, we're going to show two ways to tell this causal story. How do we tell the story? There are many ways, but we're going to show you two methods. And we are going to focus on the case where we are only interested in the causal effect of one single variable. Okay, so there is only one single variable whose effect we care about. There may be other variables involved in the model, but their effect are not what we care about, okay? Now, the first way to tell a causal story is to build a structural model. So what is a structural model? A structural model is kind of a complete, in the economics context, it's a complete economic model for the variables of interest. And the complete economic model will be self-contained, will describe the structure of how the variables are generated in that model. And then once we have this complete model, we're going to reduce it to a linear model by making simplifying assumptions. The economic model that we construct should match the data available, should match the population available. Let's consider an example to fix ideas. Suppose that we have available the sales quantity Q and the price P, as well as some market features W for a product in many markets. And suppose we want to study the demand curve. The demand curve is the curve that describes how demand changes when you vary price, holding other things constant. And this is a very important piece of information to find out, because combining the demand curve with the supply curve, we will be able to study what happens in the market in great detail. For example, we will be able to study the effect of a new sales tax, how the new sales tax will affect price, will affect quantity, and will ultimately affect the welfare of the seller as well as the buyer. So finding out the demand curve is quite important. Now, to do that, to build a causal model where we can study that causal effect, we can start with the standard economic supply-demand model. The standard supply-demand model, as you may have learned in Econ 101 or Intermediate Micro, tells us that in a market, there are buyers and seller. The sales quantity and the price are simultaneously determined by the demand and the supply. So the quantity equals both the demand, which is a function of the price, and some market demand factors, like the wealth or the number of consumers in that market. And the sales quantity is also the supply, because the supply will have to equal the demand for the market to clear. So the sales quantity is also the supply equals the supply function of the price and some supply shifters. These WS, US are some market characteristics that affects the supply. So these are, for example, the cost of supplying the product. So these are factors that may affect the cost of supplying the product to the market. Okay. All right. So according to that model, we can write down the demand equation and the supply equation. And the market clearing condition tells us that the price in that market in both the demand and the supply equation are the same. And the quantity, the demand quantity and the supply quantity are the same because the market has to clear. So here, D is the demand function and S is the supply function. And WD is the observable, is the vector of observable market factors, market features that enters the demand function. And WS is the vector of observables that enters the supply function. And UD is the unobservable counterpart of WD, and US is the unobservable counterpart of WS. All right, so after we built this model, let's say we take the demand model as an example. We want to turn it into a linear regression equation. We can do that by assuming that D is linear in these random variables. Or in other words, assume that D can be written as beta 0D, beta PD times P plus beta D prime WD plus UD. So this is an assumption. We assume that the demand function looks like this for some beta values. And suppose the supply function also is linear for some beta S, beta PS, and beta S. So if you think this completely linear model is restrictive, you can somehow relax the linearity by including some nonlinear terms of W here, and that will not affect the basic structure of the model. Now let's focus on the demand model. After making the simplifying assumption, Q becomes the demand equation. So this demand equation becomes this Q equals beta 0D plus beta PD times P plus beta D prime WD plus the arrow term UD. Here, because we have told a story of how demand is generated, so this is the demand equation. This is how quantity, how demand varies when you vary P holding other things constant. Therefore, the beta PD is the effect of increase in price on demand. And WD is WD is called the observable demand shifters. These are market features that shifts demand up and down. And UD are the unobservable demand shifters. And in order to interpret beta PD as the causal effect of price on demand, we also need to assume that there is no nonlinear term of P that are hiding in the unobservable part, so that it's reasonable to imagine changing P without changing any of the other factors. So this is how you tell a causal story using by first constructing a structural model and then reduce it to a linear regression equation. Now, what's the second way to tell a causal story for the linear regression equation? The second way is by imagining potential outcomes. And this potential outcomes framework can be applied more generally, but is especially convenient when you're studying the causal effect of a dummy variable, say denoted by D. The dummy variable of interest in this context is often called the treatment. So D equals 1 indicates the person is treated, and D equals 0 indicates that the person is untreated, is not treated. So what are potential outcomes? Now imagine one individual, imagine a representative individual. Let's not look at her treatment status, D. For now, we don't care about whether she was treated or not. But we can imagine two outcomes for the person. Y1, which is the outcome that she could have if she is given the treatment. And Y0 is the outcome that she could have if she will not be given the treatment. So Y1 is called the potential treated outcome. Y0 is the potential untreated outcome. Since Y1 and Y0 are two possible outcomes for one individual, for a given individual, the individual is fixed, is the same for the two outcomes. And therefore, all her characteristics are fixed, whether unobservable or observable. The only thing that makes Y1 and Y0 different has to be the treatment. Therefore, Y1 minus Y0 is interpreted as the causal effect of the treatment. And in this particular context with the dummy treatment variable, we call this the treatment effect. So Y1 minus Y0 is the effect of the treatment on the outcome for this particular individual. Okay, so individualized treatment effect. So how do we map this potential outcome framework into the linear regression equation that we have been talking about? We do this by first relating the observable outcome, the realized outcome, to the potential outcomes. Because for each individual, her treatment status is either 1 or 0. It cannot be both. It cannot be neither. So it's either 1 or 0. So even though the individual has two potential outcomes, only one of the potentials is realized. And that realized outcome is the outcome that we eventually observe in the data set, and we denote that by Y. Is this outcome the treated outcome or the untreated outcome? Well, it depends, right? It depends on whether the person was treated or not. If the person was treated, D equals 1, Y minus D equals 0. Then the outcome we observe for that individual has to be the treated outcome, the potential treated outcome. So the potential treated outcome is realized when the person is treated. And analogously, the potential untreated outcome is realized when the person is untreated. So D equals 0, so 1 minus D is 1, D is 0. Okay. So this equation relates the observed outcome to the two potential outcomes and the treatment status, D. based on this equation, we first collect the terms that contain D. There are two terms that contain D, y1 times D minus y0 times D. So therefore, that equals y1 minus y0 times D plus y0. Y1 minus y0 is the treatment effect, individualized treatment effect. Let's make a simplifying assumption. Assume that treatment effect doesn't vary across individuals. So it's homogeneous across individuals, or it's constant. Let's assume that this is a constant, and we use beta 1 to denote this constant. Then this beta 1 by definition is the constant treatment effect. This is of course a strong assumption and it's usually not considered to be true. We will return to non-constant effect in later lecture. But for now, let's assume this treatment effect is constant for every individual. Now, so that is beta 1. And now y equals beta 1d plus y0. Y0 is the potential untreated outcome that is typically not assumed to be constant because people are observed to be different. People are different with or without the treatment. So y0 is not assumed to be constant. It captures the heterogeneity across individuals before treatment. And now you might think maybe this is then this can be the error term for the regression equation. But we usually want to normalize the error term to have mean 0. So we're going to take the mean or the expectation of that random variable out and call that beta 0. Let that be the intercept. And let the error term be y0 minus ey0. So u now is normalized to have expectation 0. Then this equation will give us the linear causal model, y equals beta 0 plus beta 1d plus u. So that is our linear causal model, linear causal regression model that we set up in the potential outcome framework. And by definition, this beta 1 is the causal effect of the treatment. All right, so now U is y0 minus ey0. It is the demeaned potential untreated outcome. And this is, if this is a causal model, so U does have interpretation. It is the demeaned potential untreated outcome. And that summarizes a lot of pre-treatment characteristics of the individual. That's a good summary of all the pre-treatment characteristics of the individual. Now let's go back to the general notation for a simple causal regression with just one causal variable and y equals beta 0 plus beta 1x plus u. If you have set up the causal linear regression from the structural model, then the u will have meaning that's given by your structural model. In the demand case, the u would capture all the demand shifters. Okay, and in the potential outcome framework, this u will be the mean untreated potential outcome. So u in both scenarios, in both approaches to tell a causal story, u summarizes all other factors contributing to y. And beta 1 is the causal effect of changing x on y, holding all factors in u constant. Now that is our causal regression equation. How do you make sure that assumption A1 holds? How do you make sure that X and U are uncorrelated? So we normalize U to be 0, which is a normalization because we include an intercept to the model. If U doesn't have expected value 0, then we can change the model so that beta 0 capture the expected value of U, and what's left here, we can define a new error term that's the mean that has mean 0. So in general, we take this as given, as a normalization. So how do we guarantee that X and U are uncorrelated? And what to do if they are correlated? If they are correlated, OLS regression of Y on X will not give us consistent estimator for the causal effect. Then can we do something about it? Okay, so today we will answer the first question, that's how do we guarantee X and U to be uncorrelated? We're gonna present one answer to this question. And in later lectures, we'll study how to estimate the model when the orthogonality condition doesn't hold. So the way to guarantee X and U to be uncorrelated that we're going to talk about is by randomized control trial. And this RCT is the most direct way to ensure orthogonality condition. So what is RCT? There are many ways to do RCT, but in the most simple setting with a binary treatment variable X, RCT involves the following steps. First, you can draw a random sample from a population before treatment, before X is given, before X is generated. And then we divide the random sample into 2 groups according to a computer-generated random number. One group we will call the treated group, and the other group called control group. Everybody in the treated group will be given the treatment, and no one in the control group will be given the treatment. And then after the treatment or the placebo is given, if the placebo is possible for the particular experiment, and we wait some time to observe Y, and that way we're going to form a data set, yi, xi, and maybe there are other variables too, but in the most stripped down case, we just have yi, xi for all the people in the random sample we drew at the beginning, and that will be our data set. In this randomized control trial, the orthogonality condition is guaranteed. The idea is that X is assigned according to a computer-generated random number, which is not correlated with anything, any characteristics of the individuals. And therefore, X is reliably independent of all the pre-treatment variables. And suppose U contains only pre-treatment variables, as it often does, then U must be independent of the treatment. And in the week where we talked about the modes of independence, we know independence, which is the strongest independence, statistical independence, implies 0 correlation. So if U and X are independent, then X and U have 0 correlation or 0 covariance. And because we normalize the EU to 0, so the covariance between X and U is EX times U, and that is 0 due to the independence between U and X. So in an ideal randomized control trial, if the model is generated from an ideal randomized control trial, then OLS of y on x should consistently estimate the causal effect of x on y, because the orthogonality condition is guaranteed by the way x is assigned, which is randomly assigned according to something uncorrelated independent of all the pretreatment variables. Randomized control trial is kind of the golden standard to study causality in clinical study, to establish causality in clinical study for very good reason, because that RCT may be the only indisputable way to ensure zero correlation, to ensure that the effect you estimate is consistent for the true causal effect, and that is not contaminated by other factors or confounders. So like almost all the drug or vaccines have to go through extensive randomized control trial before they can be approved by the FDA. So in clinical study, that's kind of the norm or golden standard. In economics, RCT is not all that common because administering randomized control trial on in economic situations is not all that easy. For example, you cannot, if you want, when you want to study, say, the effect of education on income, in almost no regime in the world, you can randomize people's education level. It's just not possible. However, RCT has received a lot of attention in recent years and has been done a lot in contexts where they can be done. And it was actually recognized by the Nobel Committee in 2019. And the kind of RCT done in economics are typically related to public funding and international aid. Um, and the idea is that there are a lot of public funding and international aid programs available for specific purposes. For example, for eliminating mosquitoes or to provide clean water and so on and so forth. So those fundings are available to help people. There are lots of those. However, there are not enough of them, not enough funding to help everyone possible. So how do you allocate those fundings in like a fair way? Um, the idea is, why don't we randomize? If we randomize, we are allocating in a fair way. And at the same time, so we are helping people, but at the same time, we can also get a data set using which we can study the effect of the aid. If we can estimate the effect of the aid very well, then we will know how much the aid helped, whether it helped at all, whether it had any unintended consequences. Right? So this is a very simple and powerful idea, and but not a lot of people could pull it off, right? So the woman who did pull it off was Esther Duflo, and who was awarded the Nobel Prize in Economics in 2019. So RCT has been very successful in development economics. And personally, I am a believer of RCT because I think it is a good way, a very convincing way to identify and estimate causal effect of programs. But as much as we should like it, we should also be aware of many pitfalls of RCT. And today we'll just very briefly talk about these pitfalls, and I will also assign a reading for you to look at, and the reading will have more discussions of those. Pitfalls that affects the internal validity of RCT include non-compliance and attrition. So what is internal validity? So that's basically assumption A1. So whether in your sample, X and U are independent or not. So some issues can threaten that internal validity, like non-compliance and attrition. We'll talk about those in detail just a little bit later. In internal validity is kind of easier to guarantee if you administer the experiments very carefully. However, there is also the consideration of external validity of RCT, and that can be a big problem. So what is external validity? It is how how generalizable the result of the RCT is. Like suppose you run mosquito elimination program in Africa. How is the result from that experiment generalizable to, say, India? And that's a big problem. And there are many reasons to doubt the external validity of RCT, and there may also be some ways to save it. But it's in general pretty hard to guarantee external validity of RCT. And also, lastly, RCT is of only limited use because in a lot of problems you cannot meaningfully randomize the treatment, like education. You can, in almost no circumstance, to randomize the education level of people. It's always a free choice of individuals according to their own ability and their ability to afford. Now let's briefly talk about non-compliance, which is an important threat for the internal validity of randomized control trial. And luckily, we do have some ways to deal with it. We'll talk about that later. So what's non-compliance? Non-compliance means some people in the treated group do not take on the treatment. They are in the treated group. We want them to be treated, but they may not take the treatment. That's very common actually in RCT. For example, in the famous moving to opportunity experiment. By the way, for this experiment, there is a data available on this website if you want to look at. In the moving to opportunity experiment, poor people are given vouchers that they can use to help them move to a non-poor neighborhood. The idea is to study, so the purpose of the experiment is to study the effect of moving to a non-poor neighborhood on the welfare of the individual. Okay. However, people can be given vouchers, but they cannot be forced to move. So many people who receive vouchers do not use them, do not move. And the opposite could also happen. The people who were not given vouchers somehow managed to move to better neighborhood. So the causal variable of interest is moving to non-poor neighborhood, but this causal variable cannot be randomized. We want them to move by giving them vouchers, but they don't. They do not comply. Okay. So only the voucher can be randomized, but the voucher is not really the causal variable that we are interested in ultimately. So ultimately, V may be randomly assigned, may be independent of the pre-treatment variables, but M is still mostly determined by individual free choice. It's not independent of the pre-treatment characteristics. So M is not independent of U. That's the problem that non-compliance incurs. So how do people deal with non-compliance? There is one approach. Approach one is let's just surrender, right? Let's change the target. I cannot shoot the right target. I'll just change the target to something easier. We focus on the effect of intention to treat instead. What that means in the MTO example is that we focus on the effect of the voucher instead of the effect of moving. Then to estimate the causal effect of the voucher, it's easy because the voucher is randomly assigned. Okay, the causal model with the voucher as the explaining variable does satisfy the orthogonality condition. So that effect, even though it's not the effect we are really interested in, it's reasonable to think that's a useful effect to estimate, useful quantity to learn. For example, this effect is reasonably believed to be a lower bound for the actual causal effect of moving. So now that's approach one. Approach two is to use two-stage least squares. So suppose I still want to estimate the effect of moving. Can I do that? Well, you can do that, but not using the OLS estimator, but instead using two-stage least square, which we will talk about later on. Now that's the non-compliance is the first issue that threatens the internal validity of RCT. Attrition is the second threat to the internal validity of RCT. So what's attrition? So the attrition means people drop out. People drop out of the experiment by dying or by refusing to respond again before their outcome can be recorded. So say you had a random sample of 1,000 people, you administer your experiment to 500 of them, 500 randomly selected of them. Now you give them the experiment and the placebo, then you wait 5 months to then you go to interview them to observe to record their outcome. But it turns out only maybe say 400 of those who were treated can still be reached, and maybe 450 of those who were on placebo can still be reached. Then your final sample will only be, say, 850 instead of 1,000. So that's attrition. If attrition happens evenly across group, if there is no reason to believe that attrition differs across the treated and untreated group, then that is not a big problem, because the treated people and the untreated, because within the sample that are still available to you, the treated group and the untreated group are still similar. Okay, meaning that the treatment is still uncorrelated with their pre-treatment variables. So that would not be a big problem. However, if the treatment somehow affects attrition, for example, in the moving to opportunity experiment, it's possible that it's easier to follow people who received the voucher and moved, because when they move, they use the voucher, they are going to have to receive money from the government, and therefore when they submit the voucher, their moving record is recorded. So the experiment people know where they have gone. But for the people who didn't receive the voucher, when they move, they don't have to report to the government. So when they move, it's more likely that they are lost. Okay, so in if that's the case, then attrition could be different across groups. Okay, treatment could be affecting attrition. If treatment is affecting attrition, then treatment could become correlated with the pre-treatment variables. Um, and because of that, the orthogonality condition could fail. Of course, sometimes we could kind of test for correlation between treatment X and the pre-treatment characteristics within the sample that's finally available to you. And by doing this correlation test, you can somehow assess how important the attrition was, how random attrition was. If you found a correlation between X and some pre-treatment characteristics, then that's a red flag. That means attrition might have happened in a way that affects your internal validity. So how do you test for correlation? Testing for correlation is kind of simple. Say you have a W1, say you have two, let's just say you have two pre-treatment variables, pre-treatment characteristics. Say the education level of the household head, and maybe the pre-treatment income of the household. So take W1, W2 to be two pre-treatment characteristics, and X is the treatment. Without attrition, there shouldn't be correlation between X and W1 or X and W2 if there were no attrition. With attrition, if the attrition were random, then there still should not be correlation between X and W1 and X and W2. However, if the attrition is not random, if the attrition was affected by X, then it is possible that W1 and X in the final sample after attrition become correlated. So you can set up a conditional mean model of W1, W1 given X, say equals gamma 0 plus gamma 1X, and test the null hypothesis that gamma 1 equals 0. If gamma 1 equals 0, that means there is no correlation between X and W1. And you can do the same thing for W2, say delta 0 plus delta 1X, and test the null hypothesis. Test these two separately. Okay. How do you test the gamma 1 equals 0? You can use the two-sided large sample t-test. So you can use two-sided large sample t-test for each of these null hypotheses after running the regression of, say, W1 on X and running the regression of W2 on X, running OLS regression of W1 on X and OLS regression of W2 on X, and test the statistical significance of these two slope coefficients. Finally, I want to talk about the threats on external validity. There are many ways that the external validity may be threatened. The first way is maybe the sample that you draw were not representative. the sample is non-representative. So for example, say in a drug trial, they ask people to volunteer to be in their clinical trial. But the people who volunteer and the people in the general public are perhaps different. The people who volunteer may need the drug much more than the general public. Right? So if you want to extend what you find in that volunteer group to the general public, you have to be careful. It's also possible that the treatment assigned is not the meaningful treatment in the whole population. Okay, it's not a representative treatment. That happens a lot when people run lab experiments to study, say, altruistic behavior or study risk aversion or study people's patience in the lab experiments. In lab experiments, the participants, first of all, it's also not a representative sample because those also require volunteers. So, and the volunteers who sign up to lab experiments are not the same as the general population. And second of all, the treatment in lab experiment is usually just a small amount of money, and which is quite insignificant in the person's wealth. If you want to apply the risk aversion, let's say you found in the lab experiment, onto the general population, you want to argue that is the risk aversion that people have when they make life decisions, then you might be extrapolating too much, because when they make more significant, more important decisions, they may not behave the same as when they are faced with, say, $20 of price in a lab experiment. And a third important threat to external validity of RCT is the general equilibrium effect. For example, you may have heard some of the politicians arguing for giving everyone a universal basic income, like $1,000 stipend, monthly stipend to everybody in the United States, right? So that is a policy that could have non-negligible impact on the macro economy. So you could run a randomized control trial, get a random samples of 1,000 people and give some of them $1,000 every month and see what effect it has on their life. But that's not, but to generalize your finding from that 1,000 people to a universal basic income that applies to the whole population is risky, because giving $1,000 to 1,000 people doesn't matter for the macroeconomy. However, giving $1,000 to everyone in the population will have non-negligible impact on a lot of things, like inflation and shift in culture norm, and so on and so forth. So you're gonna have to be careful when you generalize a small scale experiment to a large scale policy. So well, I don't have solution to all of these problems, and there is no general solution to all of the problems. But these are things that we should be aware when we study or interpret the results of a randomized control trial. Final remarks on RCT. Clearly, RCT has pitfalls, and it's not for every researcher. Not every researcher can pull off a randomized control trial, but it helps to have RCT in mind. Even if we cannot run RCT, it's useful to imagine an RCT when we think about causal effect. Because the imaginary RCT in which the causal effect is defined give us a benchmark so that we can build upon. What does that mean? That means, say, say you are studying the causal effect of education on income. You can imagine an RCT where education is randomly assigned, and then you observe people's income. That benchmark imagine RCT can give you um, a consistent estimator of the causal effect of education. But in practice, you don't have that RCT, and you can talk about in what way the reality, the data in reality violates the RCT condition. How does it violate RCT? How is it different from RCT? And that's what I mean by using the imaginary RCT as a benchmark to build upon. And in later lectures, we will talk about some ways to base to build upon an RCT. It's certainly also useful to combine randomized control trial with other econometric tools. Other tools can be useful to correct some of the problems in RCT.